That's a good place to start. And so I posted the handout, and I've got printouts if you want them. We're going to start talking about different numeration systems, which is kind of the fun part of the course, where we move between different bases eventually. But we're going to get back to the basics, the very, very basics. And so the numeration system that we know and love is technically the Hindu-Arabic numeration system. No one knows it's called that, but that's what it's called. And so we often call it the decimal system. And the decimal system has 10 symbols, right? And so when you learn to count, you had to learn that things like 19 is what? 1 and a 9, right? And so here, if we think of it this way, right, we have 10 fingers, and so that's where the word digits comes from. Just kind of a fun thing, right? Digits. We could have even talked about different, so there's kind of Babylonian number systems where they had like little images to represent numbers, but I can't remember if they were in base 12 or 16, or 60, sorry, it's base 60, which is crazy. And so we work in base 10, and what that means is that we group by tens. So we use 10 symbols called digits, right? So here we have 10 symbols, 0 through 9. And then larger numbers are expressed in terms of powers of 10, right? And so it's positional, meaning that 10 is different from 100, right? And so not just because you have a 1 and a 0 and you can move them all around, but we know that 10 is different from 100. If we think about the number 10, we could invent a new number, but then that kind of defeats the purpose of having a numeration system. And so we could reuse existing digits by altering their position. So 10 means one group, and usually we have kind of this image, right, where we've got this block of 10, and that's what 10 means. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots, and then we can use it as a block, right? And if you go see Kate in the Learning Center, she's got all these crazy kind of visual aids so she's got the blocks of 10 and the singles and the groups of hundreds, and I don't have those, but I think that we can all get on board that 10 is one group of 10 and 0 single elements, right? And so what does that look like? That looks like one group of 10 and 0 single elements. So that's where the 10 came from. Yeah. Same idea. We know that 32 is 3 groups of 10 and then 2 extras or 2 single elements, right? And so if we have, I'm going to cheat and copy this 3 times. 1, 2, 3. Cheater, cheater, cheater. I know. 1, 2 extras. What if we have a group of groups, right? So once we reach 9 groups and 9 extras, then we do the same thing and make a group of groups. So then we could lump them into hundreds, right? And so if I have 10 groups of 10, I can make one group of 100, or what's going to be helpful is thinking about 100 as 10 to the power of 2. So what does 134 mean? 134 means one group of 10 to the power of 2, which is 100. 3 groups of 10 to the power of 1, which is 10. And 4 extras. But really, of 10 to the power of 0, right? Which is just 1. So the extras are really just the 10 to the power of zeros. So what we can do is we can use this and we can write 134 in expanded notation. We can write 134 in expanded notation, which would look like this. So 134 is the same as 1 times 10 to the power of 2 plus 3 times 10 to the power of 1 plus 4 times 10 to the power of 0, technically. Now you can drop that if you want, but I just want to emphasize that it's there. So, what if we want to write 52,613 in expanded form? Well, where am I going to start? I'm going to start by writing this out so I can see the numbers better. 5, 2, 6, 1, 3. And then I'm going to start by assigning this 3 to 10 to the power of 0. I know I have 3 extras or 3 singles. And so here, 3 times 10 to the power of 0, which means as I'm moving out each placeholder, I guess, I'm increasing my power of 10 by 1. So the next element or next digit is going to be 10 to the power of 1. 10 to the power of 2, 10 to the power of 3, and 10 to the power of 4. So as long as you start by the smallest element, and if you have a decimal, then you would start at that decimal. And spoiler alert, you can go in the negative powers of 10 in the decimals, but we'll get there. So we're going to write this in expanded form, which really is just taking 5 times 10 to the power of 4 plus 2 times 10 to the power of 3 plus 6 times 10 to the power of 2, etc. 5 times 10 to the power of 4 plus 2 times 10 to the power of 3 plus 6 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus 3 times 10 to the power of 0 is writing it in expanded form. Now I made a typo here. We're going to do this one and the one I intended to do because it's more of an example. I don't know how I messed that up, but if we want to write this expanded form in decimal form, right, making sure that you have all the powers of 10 accounted for. So here I've got 10 to the power of 0, 10 to the power of 1, 2, 3, 4, which means that I'm allowed to just drop these values out. Maybe that didn't make sense. Made sense in my brain. Just drop them all out. So 4, 2, 6, 1, 3. This should have been for more of an example. Why not? 4 times 10 to the 8 plus 9 times 10 to the 7 plus 6 times 10 to the 4 plus 3 times 10 plus 7. There, that's more of an exercise. Why? Because we have to include all the different powers of 10, right? Not just the ones that are shown, but starting at 8, I have 8, 7. I need to include 6, 5. I have 4. I don't have 3, 2. I have 1, and I have 0. So what I'm going to do is I'm going to make placeholders all the way up to 10 to the power of 8. So what I mean by that is 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10, oops, combine them, 10 to the 6, 10 to the 7, and 10 to the 8. Where I have a value, I can place it on top, and where I don't have a value, I write 0. So I have 4 times 10 to the 8. I have 9 times 10 to the 7. And then 6 times 10 to the 4. 3 times 10 to the 1. And 7 times 10 to the 0. Which means I have zeros everywhere else. Boom, 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 boom. Yeah. Nice. So a decimal, right, is used to separate the whole part from the fractional part, where 1/10 or a tenth is 10 to the negative 1, right? And so what happens is we have a decimal here, and then on either side, I'm going to have 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, But it behaves in the same way, where I just take what's on top and I multiply it by 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. And of course, on this side, I have 10 to the 0, 10 to the 1, 10 to the 2. You can't have 10 to the 0 on both sides, right? But we're concerned about the whole numbers, and 10 to the power of 0 is 1, and so that's why it has to be to the left of the decimal. 10 to the power of 3, keeps going. So we can use the same method if we want to write 479.352 in expanded notation. I'm going to write it nice and big here, 479.352. Starting at the decimal, right? Let's deal with 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the negative 1, 10 to the negative 2, and 10 to the negative 3. So in expanded notation, I get 4 times 10 to the 2 plus 7 times 10 to the 1. You can drop that 1 if you want. Plus 9 times 10 to the 0. Again, you can just write 9 if you want. Plus 3 times 10 to the negative 1. Plus, and I'm going to move this over so I can fit it all on one line. 5 times 10 to the negative 2. I still can't. Plus 2 times 10 to the negative 3. I wrote too big. Really committed. So what we're comfortable with is working in base 10, right? Hopefully this doesn't feel too bad, can handle that. And so, but what we want to talk about today is that we don't necessarily group by tens, which is what we're going to call base 10. We can group by any counting number. And so for computers, we've got some main bases that we work with. We've got base 2, which is binary, base 8, which is octal, and base 16, which is hexadecimal. Yeah. So there are subtle dots here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 dots, base 10. Right? And so now we can look at how this behaves in different bases. So you've still got 11 dots that we know what they look like. Okay, but starting at base 10, why is it 11? It's 11 because it's one group of 10 followed by one lonesome one. Right? If you were working in base 9, then your grouping would be one group of 9 and 2 lonesome ones. Yeah? This all looks fine until we get to kind of base 5, right? And maybe let's jump ahead to arguably the most confusing one, which is base 2. So let's have a look. Yeah. Or do you like it? Okay. Okay. Then sit back, relax, and enjoy the show. In base 2, if we have, let me copy these. What we're going to do, right, and it is exactly the same as when we work in base 10, but for me, I don't know, I just have a harder time with it. Okay, so I'll start with making groups of 2. So as many groups of 2 as I can. 1, 2, 3, 4, 5. And then one lonesome one. But I see that I can still group these, right? And so just like if we hit 100, we group in terms of hundreds, not tens anymore, right? And so let's see here. I've got one group of 4, I guess, and another group, and that's it. I've run out of groupings. But now I have 2 of these groups, which means that I can group them as one thing. So in terms of writing this in base 2, we're going to have one of the largest things, which is the green box. We have 0 leftovers. So all these pink boxes were swallowed by the green box, right? And so now I have 0 pink boxes left over. But I do have the next increment down. I have 1 blue box outside. And I have, oh, and I should have used a different color. Let me just do a quick switcheroo here. So it's not so. There. No harm, no foul. Then I have 1 pink one on its own. Which means 11 base 10 is 1011 base 2. And you can go through and you can do the same thing for base 3, for example, right? And so then you move through and you make groups of 3. And then if you can make another group of 3, then that's great. Then they can absorb into that bigger group of 3. And so that's why we get one big one, 0 of these little mini groups of 3, and then 2 on their own. Notice that the base is 2, then you have 2 symbols. If the base is 3, you have 3 symbols, right? And so on and so forth. And so here, in a base B system, we need to have B symbols. You can imagine that that's a problem when you hit hexadecimal, right? We just said, okay, I only have 10 symbols from base 10, so then I need to kind of get creative. Yeah. Seems like a logical choice, right?
Sure.
So if we want to change from base B to base 10, oops, you're going to write the numbers in expanded notation, and then the resulting number is in base 10. So if we want to write 1011.01 base 2 in base 10, let's do that. First thing I'm going to do is write these bigger. 1011.01 base 2. And so I'm going to use the same method as before, right? So here to the left of the decimal is 2 to the power of 0. I wrote them a little tight. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the negative 1, and 2 to the negative 2. If I write this out in expanded notation, and then I do the math as we normally would, then I'm going to get to the value in base 10. So this becomes 1 times 2 to the 3 plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0 plus 0 times blah, 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 2 to the negative 1. Need some more. Just one more. Plus 1 times 2 to the negative 2. This is 8 plus 0 plus 2 plus 1 plus 0 plus 0.25. So I get 11.25 base 10. Whee. Back to what we know and love. What if we have the same value but base 4? We do the same thing, right? But with 4 as our multiplier. So same deal, 1011.01, 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3, 4 to the negative 1, and 4 to the negative 2. One times 4 to the 3, 0 times 4 to the 2, 1 times 4 to the 1, plus 1 times 4 to the 0, plus 0 times 4 to the negative 1, plus 1 times 4 to the negative 2. I don't have it broken down, but I'm confident that you can do it and find that hopefully it's 69.0625 because I just copied it down. I don't want to write that out. Same thing, base 5, if you want to. Try it. I'll write it out, but I'm not going to read it because it's very tedious and monotonous. But I do want you to try it on your own, just to make sure you've got it. So much writing and reading if you're me. Yeah. But making you work for it. There. Oops. Five to the power of 3. That's 75. Who knows? Who knows? This is 0. Math plus 5 to the negative 2. 1 over 25.04. Get 131.04. Easy enough. What if we want to change from base 10 to base B? If you want to change to base 2, you group by 2s. If you want to change to base 3, you group by 3s. And then, I know, the etc. got chopped off onto the next page. What a waste. Waste of space, paper, I don't know. But so we do our groupings by whatever base we want. Now, there are kind of 2 common ways that you're going to move between your bases. So you could use a list or a table of powers in base B. And so something like this, where you have base 2. And so starting over here, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, blah, 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 all the way up to 2 to the power of 5. You could keep going because you have a calculator. And so then we could use something like this to figure out what the biggest possible thing that you could divide out is, and then go from there. Or repeated division. I actually kind of prefer repeated division in this case because it's easy. Just keep dividing, use your calculator. And so we're going to use both methods for this one. So we're going to convert 42 to base 2. Now, if I'm going to use the table, you would go through and, well, you know 42 is bigger than 1. So 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power, 2 to the power of 4 is 16, 2 to the power of 5 is 32, 2 to the power of 6, so we're getting close, is 64. So we see that 42 is in here, which means that 2 to the power of 5 is the biggest thing that I could take out of 42 before I run out of little dots. And so now we can rewrite this as 42 is 1 times 2 to the power of 5 plus 10. So now I need to break this down. So 10, doing the same thing. 10 is somewhere between 8 and 16. And so it's going to be 0 times 2 to the power of 4, because I can't take a 16 out of 10, but I can get 1 times 2 to the power of 3 out of it. But then I'm still left with 2, so then I have 2 is 0 times 2 to the power of 2. I'm not writing these very well, am I? It's because I'm trying to get through it. I know, I prefer the division. I know, this is using the table, and I don't like it. Because we have calculators, we can just do this. But 0 times 2 to the 2 plus 1 times 2 to the 1 plus 0. And 0 is 0 times 2 to the 0. So now I have 0, 1, 0, 1, 0, 1. Or moving down this way, wait. Okay, it kind of worked, but that's not what I meant. I know. 42 base.
Just do the ones we had to, like 2, 8, and 32, and then add zeros and everything in between. Add 0.
Is it the repeated division that you're talking about? Because that's our second example.
In the table?
Yeah, here.
42 minus 32 minus 8 minus 2. Okay, we use these 3, add 0 to everything else. This gets more confusing.
Yeah. Where was I? 1 0 1 0 1 0. Thank you. Base 2. Or I prefer, I'm going to give myself more space because I could use repeated division. The only problem is that you have to start from the bottom and then you divide up. So you kind of need to give yourself more space. So I'll start down here. 42 divided by 2 is 21 with a remainder of 0. 21 divided by 2 is 10 with a remainder of 1. 10 divided by 2 is 5 with a remainder of 0. I think you see it. 5 divided by 2 is 2 with a remainder of 1. 2 divided by 2 is 1 with a remainder of 0. 1 divided by 2 is just 1 with a remainder of 1. And now you read down.
You could have just wrote it down and then read it like from down to up.
But that's not how division, like the division symbol works. You put the remainder, or like the quotient up top.
Yeah, but if you do it like that.
Oh, you want to make up your own math.
Mine would still.
It would.
You do a slash instead of this.
I guess you, yeah.
Sign.
Yeah, what do you want to do? You want to do something
Slash.
like this?
No, just slash. What do you do? Slash 2.
That's true.
Yeah. Then you write the.
And then you would write this?
Yeah, and I equals 0.
And then you want to
I
read it
equals
from the
I
bottom?
equals 1. Yeah, I equals 1. Yeah. And then you read from the bottom.
That's true. It would save you having to figure out how many lines you'd need, roughly.
This time
Either one works. I mean, you're doing the same thing. I'm trying to, so as we're doing this, I'm trying to figure out what so your method here, like mathematically what the structure would be. Because you need some structure, right? You can't trust that you're always going to have kind of reasonable values.
just subtract.
So you were saying, okay, I stop here, so 32 is for sure in there.
Yeah.
Once. So then you write 1.
If it's 42, then the largest number will always be in there. So 32 will always be in that number.
Yeah.
Minus 32.
And then, so your method is write 1 here. One of those. Is that it?
Yeah, you get 42 minus 32, and then you go to 2 to the power 4. If 42 minus 32, which is 10, could be either, you can't minus 10 from 16, which you can't, then you just skip it. You put 0 there.
Okay.
And then 10 minus 8, you get 2. So you put 1 there, 2, you can't minus 4. And then 2 minus 2 is 8.
And where are you keeping track how many you have left? Oh, no.
Okay, your calculator will keep track that for you.
That's true. That's true. Either way, it's tedious. Oh, really? Cool.
Most like Windows or virtual Windows gives you 1 or 2. You go from like binary to stuff. Yeah, that's what I'm talking about.
I feel like there's a hex button on here. There is.
Yeah.
Hex, binary, octal.
Actually,
Yeah.
that's nice. I didn't know.
In blue. I have not played around with it. Let's see. How do I get to the blue? The blue menu. Isn't that like President's Choice blue menu? Reduce salt or something.
Oh yeah, heck, that's cool.
Yeah. Worth exploring, I think. Huh. Let's see. 42.
I don't think those calculators will have science exams though. Do that? Yeah. Well, where's the button?
Huh?
Where's the button on?
So here. So this is like a secret hex thing octal, but this one's fancier, so probably has it. Yeah, here. Hex bin oct. We gotta crack the code. Figure out how to make your calculator work for you. Ask not what your calculator. How does anyone know how to get in there?
Get second, it's blue. There will be second for maybe alpha, there's an alpha, it'll be in the top left calculator. I clicked on that, I got nothing. No?
Yeah, because that's red.
Google.
Yeah. Let's do this thing. Yeah. Oh, but I will show people online what I mean. Oh, I did it twice. We're looking at these buttons. We've got these decimal, hex, bin, octal buttons. And a lot of calculators seem to have them, but we don't know how to get to the blue menu.
It's right here.
I'm gonna check the chat and see if anyone's chimed in. Nothing. Yeah, my alpha retrieves my letters where I can store values if I need them.
Yeah.
And then we need to figure out how to use it.
That's what I was doing. You didn't listen. Oh, there it is. See, I told you I didn't know how to with your calculator. Mine doesn't have it.
So how do we use
Oh,
it?
there you go. So you go base N. So you hit your menu setup.
Okay.
You go 3, and then you can click between the
blue one, two.
Whoa. Okay.
Use it in this calculator, even though I didn't have it.
So I think we went this button first, right? Okay.
You can, okay.
Menu setup. Sorry, there.
Oh, wait.
And then
3.
3.
Or, yeah, like you need to put a different picture. The one with which shows on the
Yeah.
display.
With all the, well, 3.
Delete this big picture.
Then I have to take another picture. And then you can move through and change it to, what were we doing? Copy binary, for example. So 42.
I have the thing set up. So you go menu
Whoa.
setup, right? And then you just type in, you say, you want the decimal number 21 into hex. So you type in 21, hit equals, and then you can just scroll through the 4 options. I'll show you what I have.
Good like calculated.
So I press it.
Now I'm stuck in that.
Press menu setup.
Yeah.
Now change it. It's like
One.
Yeah.
Nice. Okay, now I want to get back. So 42. I'll put 42 on my screen. Menu setup 3. Didn't keep it.
Yeah, you have to
42.
set going into it.
And do I have to tell it it's decimal?
I don't think so. You just go, so what do you try?
And then equals, and then, okay, let's see.
You hit equals, and then you can go to like hex, which is 2A, binary, which is 101010, and then octal, which is 2.
Cool. Very cool. Okay. So from menu 3, I'm gonna go decimal. Enter 42. And then hit binary.
You could probably look up the instruction manual online.
Yeah.
And it'll,
There's actually instructions on the back.
1 0 1 0. Well, this eliminates basically the rest of the class. So does everyone have a calculator that does it?
I still knew how to work it on his calculator.
Mm.
He didn't. You took long with it. With internet, that tells you how slow you are.
Because look at the examples we're gonna do. Change this base 2 to base 10. Change 47 to a binary numeral.
Might be a little bit late.
You can do all this.
You can probably already do all that.
I know. When do you learn it?
Like,
Yeah, I know. And it's always at the end. It's always at the end of the course.
It's like the
You
first
learn
lesson.
binary and hexadecimal, like that's like the first thing you learn in most classes, in most computer science classes is binary. And then you
Yeah,
go to
so my
hexadecimal.
question is, why do I have to teach it when I don't care about it?
We don't know.
I care, I
We can just
guess.
leave it. We can have 2 whole weeks free.
I was very confused.
Good.
We were doing a harder version of like conversion to binary.
Have you done Carnot maps?
What's that?
Okay, fine. We're doing Carnot maps on Friday. But on the plus side, that's the last thing that we have to do.
Today?
So we have.
No, I don't have it prepared today.
No, this is the
Change
last thing you're doing
Base
today.
2 to base 10.
Yeah, I mean, let's figure it out. So if I'm in binary and I change and I enter 1 1 1 1 0, and then I switch over to binary equals, and then I switch over to decimal, I get 14 base 10. Did I do it wrong?
So that's 14.
That's what I got.
I have a quick calculator. You have a bigger calculator.
So then I did, or actually, I was in binary. And then I entered 1 1 1 0, and then the equal sign, which I don't have a picture of, but I think you get it. And then I moved to base 10. And told me that it's 14. Whee!
Do we only have to know between like
Binary and
decimal? We have to know octal as well.
Yeah,
and hexadecimal.
and hexadecimal. So 10 to 8 and 16. That's what we need to know. Or that's all I care about. 8.
We haven't used it in any of the classes yet. And I think that's the least one that's used.
Yeah. It's on
Because
the
we
list of
use,
things I have to teach.
Because like hexadecimal is using IP addresses now.
ASCII code.
Mm.
So it's like starting to get like easy.
Just give you the answer. So 47. So if I go to the decimal and I enter 47, or clear, 47 equals, and then I move to the binary. Hey, it didn't do it. Decimal 47 equals binary. I get 1 0 1 1 1 1 base 2. Hey, it works. I've checked everyone else's calculators. Well, you won't have that on the test though.
I have one more calculator. That one has it. It's a business
Yeah,
test.
so this one has the.
I don't know if you can use an actual program.
It doesn't program calculator. It just doesn't have the scientific. It's even dumb than this one. But it has the decimal shit.
Oh my god, what did I do? Really complicated calculators. You can go, you can mess something up in the notes and you'll never figure out how to fix it.
Yeah, pretty handy. They have the newer version of this one. But just to show you how it works.
13 plus 95. That was
Yeah, I'm like, hey, what's left then? ASCII. I was gonna get you to write cat in ASCII. And then combine it, convert it to binary.
You have to add all the numbers or just write them.
Pardon?
You have to add all the different ASCII codes.
You can go over ASCII.
Like, do you wanna memorize all the ASCII codes? No.
You have to add them, so like C is 95.
Oh, let me.
C is not 95. C is 99.
Yeah, lowercase.
C is 65. A is 65.
Lowercase c is 99. Lowercase a is 97. But you know they're not the same. Uppercase and lowercase. And t is 116. It's not on here, but let's write that down. 99, which, so ASCII binary, I'm just gonna steal it. 0, 1, 1, 0, 0, 0, 1, 1. $97 and T is 160. One, 2, 3, 4. And then 0, 1, 1. 1, 0, 1, 0, 0. I don't think you add them because they're each a byte. Off, on, off, etc. How about binary arithmetic? Is that been there, done that? Or should we talk about it? All right, let's jump there. Binary arithmetic. Kind of starting here, I guess. We only need addition and multiplication because subtraction is a special case of addition, but also we're not gonna use it. So for binary arithmetic, we only have zeros and ones. Now, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1, 0. Because 1 plus 1 is 2 base 10, which is 1, 0 base 2. For multiplication, so here we have addition. For multiplication, I can do the same thing. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. So multiplication is fun. Addition.
Like if and if both of them are true, then it's true.
Then it's true. Yeah, it's like an and statement. If I want to add 1, 1 base 2 and 101 base 2, I have 1, 1 plus 1, 0, 1. I'm going to stack them like this. 1 plus 1 is 0, 1, because it's, let's call it 10, right? 1, 0. So then just the same way that addition works always, I put the 0 down and then I have 1 plus 1 plus 0. 1 plus 1 is 2, which is another 10. So then I get 1 plus 1, which is 1, 0. Oh, on your calculator? Nice. That's awesome. What about multiplication? 1, 1 base 2 times 1, 0, 1 base 2. Starting here, just the way multiplication works, right? 1 times 1 is 1, 1 times 1 is 1, 0 times 1 is 0, 0 times 1 is 0. I guess I could have written it 101 times 1, 1. It's a little bit weird looking. 1 times 1 is 1, 1 times 1 is 1. But now I need addition here, right? I need to add these all up. Did I miss one? Well, it's because I wrote them all weird like this. I should have written 1, 0, 1 times 11. But instead I went like this. That's weird. One plus nothing is 1. 1 plus 1 is 10. It's not what I have in my notes. That's why I'm. Yeah. Where did I go wrong?
You didn't put 1 or 0 up in the third row.
Here?
So,
Where do you want
there
it?
should be 2 zeros below that. This should be 0 and move the 1 way.
Please stay on the line. Okay. One. Yeah. There. Thank you. Now, 1 plus 1 is 1. 1 plus nothing is 1. I didn't say the right thing initially. 0 plus 1 is 1. 1 plus nothing is 1. Base 2. And I'm going to scoot this up. And maybe shrink it down a bit. I'll try to be more careful with this next one. 1, 0, 1, 0, 1, 0, 1, 1. So you can multiply and add in there as well? Wow. Yeah. Very cool. Very cool. I don't think I have the base and button though. It's not ringing a bell. I'll have to look into that. This isn't too bad though. As long as I keep my head in the game and stack them properly. Yeah, where did you guys get to? I have 1, 1, 0, 1, 1, 1, 0 in my notes to check against. Nice. Nice.
It's so powerful now, like, you just press a button and just get from binary hexadecimal.
And that's really what math is all about. I'm just glad I was able to give you something. But you guys told me about the, well, actually, I feel like I remembered that there were these buttons. Then I opened up a can of worms. It's worth pursuing. Octal and hexadecimal numbers and conversions. So in general, when we convert between two non-10 bases, we use the decimal, so base 10 as a gateway. Something tells me, I guess going from 7 to base 5, base 7 to base 5, you have that fancy base button. Yeah, probably not the weird ones, just the go-to ones. So you would have to convert 3, 4, 6, 4 from base 7 to base 10, and then from base 10 to base 5. So 3, 4, 6, 4, base 7 to base 10 to base 5. Oops. Should use words. Base 10 to base 5. Or do you have some secret method? No? I'm into it. I don't know the secret methods. To go from 3, 4, 6, 4, base 7 to base 5.
dividing.
Yeah.
And then whatever the numerator you get, you do it that.
I'll do it this way and then we'll check against. I feel like dividing by 5 isn't gonna work. But, so I have 3 times 10 to the power of 4, right? So to convert, or sorry, 10 to the power, that's not it at all. 7 to the power of 4, because it's base 7. Okay, I tried to go fast and I'm not a fast person. 7 to the power of 0, 7 to the power of 1, 7 to the power of 2, 7 to the power of 3. Which means I have 3 times 7 to the 3 plus 4 times 7 to the 2 plus 4 times 7 to the 1 plus, oh, I got hung up on 4s, sorry. 6 times 7 to the 1. Well, there were a lot of 4s, I guess. 4 times 7 to the 0. Now, I do have to use my calculator. And menu 1. 7 to the power of 3 is 343 times 3 is 1029. And 7 to the power of 2 is 49 times 4. $1029 plus 196 plus 42 plus 4. I get 1271, and that's in base 10, which we know and love. Now I can use that to convert to base 5. I'm going to try to use your cool way. But how? You want to do 1271 divided by that, maybe. That should be a thing. If I divide 1271, so 1271 base 10, if I divide it by 5, I can figure out right? How am I going to do this? Divide it by 5? 1271 divided by 5, 254 times.
What did you get in the decimal?
0.2.
Divide that, 2 divided by 5, that's the number. And then the number in the front of decimal, you use that for dividing by 5 again.
Show
Until
me.
you get 0 divided by 5.
Show me how you do it. I want to learn your ways, your crazy ways.
Yeah, let me try. I haven't used it in this time.
Busted.
Yeah, here's myself.
I was finishing up the one before this. I was trying to find the decimal in my calculator. I found new things instead of that.
That's pretty good. Only because I don't want to make a table of values. Right? 5 to the power of 3, maybe 5 to the power of 4, 5 to the power of 5. Okay, fine. 5 to the power of 4 was 625. 1271. You know what? What if I try it? What if I try my easy way? But I'm gonna need to write down here. 1271 divided by 5. Oh, I need the right number in there. Is 254. And 254 times 5 is 1270, so the remainder is 1. $254 divided by 5 is 50, and 50 times 5 is 250, so I have a remainder of 4. 50 divided by 5 is 10, with a remainder of 0. 10 divided by 5 is 2, with a remainder of 0. Oh, that's not true. 2 divided by 5 is 0, with a remainder of 2. So is it 20041 base 5? It is, but where can I put this? I did not do a good job spacing this out, did I? Ah! Oops. Whee! It belongs there. So then I get 20041 base 5. Now, did I? But our calculator can't help us here. But let's see. Will it work? No, I don't think so. Divided by 5. It's not gonna work. I don't have a special base button. You can go from base 7 to base 5.
I found it like 5 minutes ago.
Oh,
when I
nice.
was Finding everything else.
Nice. Then you can check my work. See if it's true. I didn't fill in my notes because I didn't think we'd get this one.
Mine is one grade below all your calculators, but that still has that.
No, isn't that the new one?
Pretty sure
That's the new version of this one, I think.
then I don't have the degree version.
Oh, 300 ES.
It's one below.
Is that one?
Yeah, you guys are 900.
You want to do?
No,
Oh,
We have it.
yeah, you can. But we would have had to do binary matrix multiplication, which kind of works, but you'd have to ignore anything that's not a 1, just convert it to a 1, basically. Okay. Octal 8 symbols, but something tells me you're comfortable with that.
Oh, right.
It's base 8. Presumably 0, 1, 2, 3, 4, 5, 6, 7. Done.
It's a decimal. IP4 is decimal.
To go from binary to octal, you're going to divide the binary digits into groups of 3 digits, starting from the decimal point, and then you're going to add leading or trailing zeros if you need them. And then you're going to convert each group of 3 binary digits into 1 octal digit. So if we have to convert 1, 1, 0, and then 1, 2, 3, 1, 2, 3, 0, base 2 to base 8. What do I get? Starting from the decimal, which is this rightmost value, and then leading zeros as needed. Now I'm completely blanking because I didn't write this down. Eight? You tell me. How do you go from base 2 to base 8? Well, how do you do it? That's a good question. So we could do it using 10 as our gateway, but I'm just totally blanking on what this is. Who has a fancy online calculator? I know you do. It was aimed at you. What's 1, 1, 0, 1, 1, 1, 0, base 2 and base 8? Start there.
In total, that's decimal is 134.
174 base 8.
Oh no, is it? Because you did like the 3
Oh.
ones, it just
Okay, thank you. Yeah.
0, 1.
So this is 110.
Yeah.
Converting each binary
The one you have
digit.
written down and the one in the function. Nothing.
This is wrong.
Yeah. Because you did the 3 instead of just 2 of them, instead of doing 4 numbers in one bracket, you did 3. That confused me, so I had the wrong answer the first
Isn't it
time.
156? Yeah, it's 156. So your first set there where the decimal would be is 0, 2, 4. So that's a 6. And then the next one, you do the same thing. 1, nothing, and 4 would be the 5.
Whoa, slow down. So this is 2 to the power, well, let's start here. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So 4 plus 2.
We're doing that.
Thank you. Thank you. Now, this one starts at 2 to the power 0, 2 to the 1, and 2 to the 2 again, right? Nice.
Then you want like the
So 1
decimal
times
number.
4, 0, 1.
You didn't want the decimal number. I was giving you
The-
the decimal number.
Like base 10?
Yeah.
Oh, no, we're using this kind of cheater way. So you could do that. You could go from base 2 to base 10 and then to base 8, and that's totally fine. But now, if you want to go straight from binary to octal, what you do is you divide your binary digits into groups of 3
Yeah, we do this in
And-
like Unix.
and then convert those groups into, thank you. Yeah, I feel like to convert from octal to binary, hexadecimal, 4. It's way later. You can take a nap. Okay. Then we have 2 to the 0, 2 to the 1, 2 to the 2, which is just 0 plus 0 plus 1, which is why we get 1. 1, 5, 6. Phew. I'll let you try this one on your own. How about? I'll write it out, but I'm not going to read it out because it trips me up too bad. Or maybe I can't help it. There. So starting from the decimal point, we make our groups of 3. Let's see if I can be not too fast, but faster. 1. 2. 2. Oh. 2 to the, this one I'll have to do. 2 to the -1, 2 to the -2. Or maybe it doesn't matter. Tell me. D-May. Or do you just keep going with the usuals? Doesn't matter. 2 to the 2, 2 to the 1, 2 to the 0.
125. It changes the number.
So is it 0.12, 12.2? Is that it?
Yeah.
Nice. Thank you. Okay. So you don't need to worry about the negatives. Moving the opposite direction is the same. Let you work on those, but let's talk about hexadecimal. Here. $16 symbols. 0, 1, 2, 3, 4, 5, 6, 7. 8, 9. It's your 10. A, B, C, D. I need 6, 1, 2, 3, 4, E, F. And now you're going to do the same thing. You're saying, but groups of 4. Let's see here. Do I have it in me? Probably not. It's been a long day. 1, 1, 0, 1, 1, 0, 1. Groups of 4. Starting from here. Create groups of 4. See ya. Thanks for your help. Everyone's been so helpful today. Oh, not 2 to the power of 4. Sneaky. 8 plus 4 plus 1 is 13. But 13 is 10, 11, 12, 13D. Same deal. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. I've got 4 plus 2, 6. I know. I heard you. Oh no, don't worry. But I want you to know that I knew that you knew. Same thing. If you want to go back to binary, then you have to convert each hex to a 4-digit binary. And then you're going to combine them, smush them together. All right, let's do this one. C45. C is the same thing as 11, 12, 13. Four is 4 and 5 is 5. 13 in binary is what? I have to do it. Thing you don't like.
Yeah.
13 divided by 2 is 6 with a remainder of 1. 1, 1, 0, 1. Thank you. 2 goes into 6 3 times with a remainder of 0. 2 goes into 3 once with a remainder of 1. And 2 goes into 1 0 times with a remainder of 1. There. 4 is 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 and 0 times 2 to the power of 0. Right? 1, 0, 0.
1, 0.
1, 0, 1. Are you on 5? Oh. Thank you. So then this becomes 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, base 2. Yes? Oh no. 10, 11, 12. Ah. In red to punish myself. But then, couldn't I just do that? This is all wrong. What's right for 13, wrong for 12. But you get the idea. I hope. Since you're correcting me, I feel really confident that you get the idea. Thank you. Mm.
Another 0 after as well, I think. because
Yeah,
we get
you need 1 more
12
0,
parts
you
of
need 2
4.
more zeros
Yeah.
in total.
Here, right?
No, in front
In
of
on
the
the left
1,
side of the 1.
in front of 100 and in front of 101.
Here. Oh man. Okay. I've got this. One one zero zero 1 0 0 0 1 0 1 base 2. I give up. These are all the same. I'll fill in the answers because I do have them. I am not going to do them personally. I'm just going to copy them down at this point. So you've got lots of practice, but you guys know what you're doing. So good job. If you have any questions, don't ask me because I don't know. And I'll see you on Friday for Carno Maps. All right, I'll stop this. I should have said that.